Hi everyone, welcome back. Myself Ayush Tripathi. Currently I am working as a mentor at GeeksforGeeks and I welcome you all to this post-analysis video of last weekly contest 178 and talking about the problem difficulty level. So the first three problems were from easy to medium level and the last problem was a bit hard and it uses the advanced data structure which is a segment tree with the lazy propagation which gonna the prerequisite for the last problem. And for the first three problem there is no prerequisite at all. So let's just quickly start with the first problem. Find minimum cost. In this problem you will be given an integer array A of length n and you want to randomly pick two numbers from the array and you need to ensure that the sum of two numbers is always even. And to achieve this you may modify any element of the array by either incrementing or decrementing it by 1, where the cost to change an element x is equals to x itself. And we need to determine the minimum total cost required to modify the array such that any randomly selected two numbers have an even sum. So let's just look at the first example. So for this array of size 4, the best is to increment element 1 by 1 so that all the elements will change to 2. Now if you pick any two random elements then their sum always equals to even. And the cost of doing this operation is the element value itself, which is 1. So that's why here the expected output is 1. And this is a fairly easy problem. And to solve this problem, you just only need to know the basic properties of math. That is, a sum of two even number is always even, and the sum of two odd number is always even. So these are the only two possible cases we have. And if you add odd and even, then the result is always equals to odd number. So we don't want this thing. So now we are just left with only two possibilities, that is either change all the elements to even or change all the elements to odd. And to achieve this, you only need to perform one operation at max at each element. Because if you add 1, then the element parity would change. If it is odd, then it will just simply change to even, and if it is even, then it would just change to odd. So at max one operation at each element. So let's just first find the odd sum and even sum. This will be my answer. So my answer, and the cost of performing operation over some element is the element value itself. So that's why my answer equals to minimum of odd sum, that is sum of all the odd element, comma even sum. Either I will change all the odd elements to even or I will change all the even elements to odd. And since we have to minimize the cost, so that's why I'm taking the minimum of these two. Cool. And what are the odd elements we have? So we have 5, 3 and 9. And the even elements 2, 4 and 12. So odd sum, which is equals to 5 plus 3 and plus 9. Then even sum, which is 2 plus 4 and plus 16. So this odd sum is 17. And this even sum 2 plus 4, which is 6 plus 12, which is equals to 18. So here this odd sum is less than the even sum. So I will change all the odd elements to even by incrementing it by 1. So just simply increment this 5 and change it to 6. Then this 3 to 4 and this 4, not 4, this 9 to 10. Now all the elements are even. So no matter which element you will pick, their sum is always even. And this is the complete approach. Let me just show you the implementation. So this is the method minimum cost that you have to complete. And here I have declared two variables, even sum and odd sum. Even sum will store the sum of even elements and odd sum will store the sum of odd element. Then iterate over this vector A, and for every element x, if it is odd, then adding its value in an odd sum, otherwise in an even sum. So this is a bitwise operator. I am taking AND with 1 because this is the property of odd number, that is LSB is set. And for all the odd number, the LSB is set. And if LSB is set, that is 1 and 1 is true. So this if condition is true, so I'm adding its value in an odd sum. And finally, I'm returning minimum of odd sum, comma even sum. The time complexity is linear, that is order of n. And since I have not used any extra space such as a string or vector. So the extra space or the space complexity is constant. Cool. So let's just try to submit this. So successfully submitted. So this is the second problem of the contest. In this problem, you are given a triplet of numbers A, B and C, and a triplet is considered balanced if the sum of any two numbers is equals to the double the remaining third number of the triplet, and our goal is to make the triplet balanced by performing some operation. In each operation, you can choose any one number from the triplet and increment or decrement it by one, and you need to report the minimum number of operations required to make the triplet balance. So for this first example, the value of A as 4, the value of B is 10, and the value of C is 5. So if you change this C to C plus 2 by performing two operation, then the sum of two integers A plus B is equals to twice of this third integer C. 4 plus 10 is equals to 2 into 7, where 7 is the new value of C. So let's see how we can solve this problem. So we have three integers A, B and C, and the sum of any two integers must be equal to the twice of the third integer. So we only have three possibility, that is sum of A plus B is equals to twice of C, or sum of A plus C is equals to twice of B, and the last one B plus C is equals to 2A. So I will try to satisfy each of the three expression, and whichever takes the minimum number of operation, that will be my answer. So let's just take this first expression for a reference, and the same thing is goes for the rest of the two expressions. A plus B is equals to 2C. So this can also be written as a 2C minus A minus B is equals to 0. If this is true, then this also must be true. So let's call this as difference minus A minus B, and let's say this difference is not equals to 0, and instead it is equals to 4. So this 4 is a positive even number. I will also discuss the case for a negative even number and for odd number. What if the difference is odd? So we have to make this difference as 0. So what I can do, I can change this C to C plus 2, because here we have a factor of 2 with C. Here we have 2C. So if you change this C by 1, then your difference will increment by 2, because here you have 2C. So that's why I have changed this C to C plus 2. Cool. So 2 into C plus 2 minus A minus B is equals to 4, and 2C plus 4 minus A minus B is equals to 4, and this plus 4 and this plus 4 will get cancelled out, and 2C minus A minus B, this was my initial difference, which is now equals to 0. So can I say this thing, if my difference is even and positive, then my answer will be equals to difference divided by 2. This will be my answer. Cool. And what if the difference is negative? So let's say what if it was minus 4. So in that case, instead of incrementing the value of C, I can decrement the value of C. That will reduce my answer by 2 into 2. So here I will change this C. If it was minus 4, then I will change C to C minus 2. So in short, my answer is absolute difference and divided by 2, because incrementing the value or decrementing the value, both will cost you one operation. So absolute difference and dividing it by 2. Now let's just also analyze the case when the difference is odd. So we have difference as 2C minus A minus B, and let's say it is equals to 7. So if it is equals to 7, then what I can do, I can perform 3 operations on variable C and 1 operation on variable A. So that is increment C by 3. So C to C plus 3, and then perform 1 operation because we have 2C. That's why we can only subtract the largest even number from this difference. And then change A to A minus 1. Now 2 into C plus 3 minus A minus 1, new value of A, and minus B. You can also perform this operation on B, and it is equals to 7. So 2C plus 6 and minus A plus 1 minus B is equals to 7. So this 7 and 6 plus 1 7 will get cancelled out, and now my difference, initial difference, is equals to 0. 2C minus A minus B, which is equals to 0. So in short, I can say my answer is equals to absolute value of a difference and dividing it by 2 and taking its seal value. Cool. So if it is even, if the difference is even, then its seal value is equals to difference by 2 itself, and if it is odd, then we are performing one operation on variable A or variable B. So this is the complete approach. Let me just show you the implementation. So here I am having my check function for variable with parameter x, y, and z, and this is parameter c, then a and b. So then we have the same expression. I am finding the difference 2c minus a minus b, and my answer is a seal value of difference by 2, that is difference plus 1 divided by 2, and floor value of this expression, or you can say seal value of difference by 2. Then this is the method that we have to complete with the parameters a, b, and c, and I have initialized my answer with some large integer, and then I am passing this a as c, then this b, and then I am checking for c, and I will take the minimum of all the three expression, and finally I am returning this answer. The time complexity is constant. So successfully submitted. So this is the third problem of the contest, round trip. In this problem, Geek is planning a round trip through cities connected by roads, forming a tree with n nodes and n-1 edges, where each city I has an excitement value a of I, and each bidirectional road g of I is connecting two cities uv with the length g of I, 2. And Geek first select a subset of cities to visit, then he design a round trip route that start from one of the selected cities, visit all the chosen city, and return back to the starting city. When Geek visit a city for the first time, his excitement increased by a of I, that is value at that node. However, subsequent visit of the to the same city do not add excitement, and traveling between two cities U and B via road of length len decreases his excitement by this integer len each time he travel along that road. And we need to report the maximum possible excitement Geek can have at the end of his trip. And one thing to note, we don't have to maximize the number of visited node. So let's just look at to the first example. So this is an underlying tree structure for the first example. So to maximize the excitement, what we can do, we can start with node 1 and then visit node 2. So how much cost or what will be the total excitement? So in this case, a of 1 plus a of 2 and minus the length of this route, which is 1. And since we have to return back to the same node, so we have to visit this edge twice. So 2 minus 2 into 1, which is equals to 4 plus 2, that is value at the nodes, minus 2, which is equals to 4. This was same as the expected output. And this is the second example. So in this case, to maximize the excitement, what you can do, you can start with node 2 and then visit node 3 and then again return back to node 2. So in this case, the total excitement is A of 2 plus A of 3, which is 3 itself, and A of 2 is 4, minus 2 into 1. That is, we have to visit this edge, which is from 2 to 3 twice, so that we return back to the same node. So 4 plus 3 minus 2, which is equals to 5, and this is same as the expected output. Now let's see how we can solve this problem, and this is a pretty amazing problem. So let's say you have selected some subset of the tree and you have decided to visit all the nodes of this subset tree. So let's say we have started from node 1. So what will be my total excitement after visiting all the nodes and returning back to the same node 1? So let's say this is your starting node. So in this case, the total excitement, or I can say my answer, will be A of 1 plus A of 4 plus A of 7 plus A of 3 plus A of 8 and plus A of 9. That is sum of all the nodes. And minus, I have to subtract the length of each edge twice, because if we are visiting some edge and then we have to return back to the same node, then we have to visit the same edge again. So that's why we must have to visit each edge twice. And the length of edge from 1 to 4 is 5. So I can say minus 2 into 5, then minus 2 into 1, the length from 1 to 7, and minus 2 into 2, the length from 1 to 3 is 2, and minus 2 into 2, and this 2 because of this edge from 7 to 8, and then we have another edge from 7 to 9, which is of length 3. So minus 2 into 3. So this will be my total excitement, and our goal is to maximize this thing. So how we can maximize this thing? So for this, let's just define a dp. So dp of u will simply store the maximum possible excitement that we can achieve if we start from node u. Node u. And since we were allowed to start from any node, so my answer will be maximum value of any node u. So my final answer will be equals to maximum of any node u, that is a summation u from 1 to n, that is nodes are numbered from 1 to n, and the maximum value. So dp of u, since I was allowed to start from any node. Cool. And what will be the transitions? So let me just write this thing over here. And again, let me just remind you one thing, that it was not asked to maximize or minimize the number of a visited city. The only concern, we have to maximize the total possible excitement after visiting some subset of the tree. So this is very simple. Let's say there is an edge from u to v. So let's say there is an edge from u, current node u, to current node b. So when I will visit this node v, so dp of u, and I will initialize this dp of u with a of u, that is to the value of node, because if you are starting from the current node and ending at the current node, then you don't have to visit any edge. So in that case, the maximum possible excitement is node value itself. And then I will add or then I will visit, now please try to pay more attention, then I will visit its neighbor if the dp of its neighbor value is greater than 0. That is a dp of u plus equals to maximum of 0 and comma dp of v if there is an edge from u to v, dp of v, and let's say this length is len, this length is len, so minus 2 into length. I know I have to visit this length twice, so this will be the transition. And if this value is greater than 0, if this value is turns out to be greater than 0, then I will add, or you can say I will visit this subtree. Cool. And this is the complete solution. Now let me just show you the implementation. There is no edge cases at all. The only observation, I will visit its neighbor if its excitement value is greater than 0. And definitely before this thing, I will call a DFS function. I will DFS function for node V, and the parent node is now U. This is basically a very trivial DFS function over the trees. And after this DFS function, I know that I have the result. I have this length. So now just compute the value of this expression and take the maximum of this expression value, comma 0. If it is 0, then I do not visit node V. And your answer will be the maximum of all the values, all the DP values. So here is the implementation, and this round trip is the method that you have to complete. So here just I have formed this is a 2D vector of pairs, which is an adjacency list, and then I iterate over the edges, which is n minus 1 edges are there, so that's why less than n minus 1 from 0. And this is the current edge from u to v with the length g of I comma 2, and then I have decremented u and v so that it will be converted to a zero based indexing, and then adding these values in adjacency list. Then here is my dp array, and then I'm calling this DFS function from node 0, and its parent, imaginary parent, is minus 1, then passing this adjacency list and dp and vector a to get the values of the node, and my answer is maximum value of dp. That will be my answer, and finally I'm returning this answer. So this is a DFS method, which is very straightforward. dp of u is equals to a of u, then I iterate over all its neighbor, and there is an edge from u to v with the length len, and if this node is a parent node, then just simply continue. Otherwise, call this DFS function for the neighbor, and after returning from the neighbor, I know the value of dp of v. So dp of v minus 2 into length, and if this value is greater than 0, then I will add it in my dp of u value, because we don't have to minimize the number of node visited. We can visit as many node as we want to maximize the excitement. So if anyhow it is greater than 0, then I will visit this subtree that is starting from the neighbor. And the time complexity is linear since I have visited each and every node exactly one time. So let me just try to submit this. So yeah, successfully submitted. And now let's just discuss the fourth and the final problem of this contest. So this is the last problem of the contest. You are given an array A containing n integers, and you are required to handle q queries provided in a 2D array. Each query can be one of the following type. The query of type 1, where you have to update all the elements A of I to A of I XOR X in the subarray from L to R. The query of type 2, where you have to find the sum of subarray starting from index L to R under modulus 10 power 9 plus 7. And for this problem, the prerequisite is segment tree with a lazy propagation. So make sure to watch some video or read some article. Otherwise, you can skip this problem. So let's just see how we can solve this problem. So we have two types of query. The query of type 1, where 4 integers will be given to you. 1, that is, which simply represent which type of query it is. Then L, R and X. So you have to update all the elements A of I to A of I XOR X in some subarray starting from index L to R. Let's say L is equals to 3 and R is equals to 7. That is from index 3 to 7. And the query of type 2 has 3 integers, 2 which represent its type, basically the first integer, and then L and R. So for this type of query, you have to find the sum of subarray starting from index L to R under modulus 10 power 9 plus 7. Because answer can be very large, so we have to take a mod with 10 power 9 plus 7. Cool. So how we can solve this problem? So to solve this problem, we can create a 2D segment tree. That is, at each node of a segment tree, I will also store the number of bits in that particular range. And we all know the size of the segment tree. It is 4n, where n is the size of array, and multiplied by 30. Because in this array A, all the elements can be up to 10 power 9 plus 7. 10 power 9 only. All the elements can be up to 10 power 9. So 2 power 29 is greater than 10 power 9. So that's why at max 30 bits will be there. So that's why I have created the second dimension of size 30 only. So now let me just again quickly remind you, each node of a segment tree will also store the number of integers which have ith bit set in that range. So let's say we have to perform some updation. So that is, we have to update all the elements of the subarray from 3 to 7 with x, and let's say the value of x is 5. So at max this x have 30 bits. So let me write the binary representation of 5, so which is 0 1 0 1. So this is bit 0, bit 1, bit 2, and bit 3. Cool. So here this bit 2 is set. So I will first find, I will just simply check how many integers in this range have the bit 2 as set. So let's say there are y integers, y elements in a range which has bit 2, that is bit at position 2 is set. So if you take a XOR with x, then after taking XOR, how many elements will be there which has this bit 2 as set? So we all know that is 1 XOR 1, which is equals to 0, and 0 XOR 1, which is equals to 1. So how many number of elements will be there? So the number of elements is simply equals to L R minus L plus 1. Cool. So the new number of elements which have this bit 2 as set is simply equals to length of this range, that is number of elements in this range, minus this y, because all the ones will be converted to 0 and all the zeros will be converted to 1. So that's why I have just simply subtracted y from here. Cool. So in this way I will update my segment tree. I will perform the update query, and how much time it will take? So if you use the lazy propagation, then range query update will take log of n base 2 time. Log of n base 2 time at max. Cool. And how I will answer the query? So to answer the query, if I know the number of set bit, if I know the number of elements which have ith bit as set, so then I will simply increment my answer by 1 left shift I time. So let's say the range is having y number of elements which are having bit set at position I. So I can just simply multiply y with 1 left shift I. Cool, because this is the weight of bit I. And how much time it will take? So again I will answer the query in just log of n base 2 time at max. These are the properties of a segment tree, and this lazy propagation is an extra feature that we have added, because the segment tree can only support point update, that is update only one element in an efficient time, and if you want to update the entire range, then you must have to implement this lazy propagation technique. So answer queries in log of n base 2 time. So yeah, this is the complete approach, and let me just show you the implementation. So this is my node class where I have this vector bits, and this is the constructor. So whenever I create a object of this node class, this constructor is automatically called, and here I have just assigned the size of this vector bits with 30 and setting all the values to the 0. Cool. So then here is my segment tree class, and where I have this vector of node object, and this is initially empty, and then we have this lazy vector to efficiently handle the range update. Then we have this mod, which is 10 power 9 plus 7, and this is n, which is the size of array a. So this is the constructor. Yeah, this is the parameterized constructor, and here I am passing this, taking the size of array a, then initializing this attribute of class with the parameter, and this is the size of segment tree vector, which is 4n plus 1, and this is the size of lazy propagation vector, which is also 4n plus 1. Cool. And how I will pull the changes to the downward. So this is simply iterate over all the integers from 0 to 29. Basically 30 bits will be there at max, and the number of elements which are having bit set in its left subtree plus the number of elements which are having bit set in its right subtree, and their total range total will be my current answer. And then how I will propagate, this is for a lazy propagation part. So this is the index, and basically the current node, then low and high range value, and this is the value which we have to update. So just iterate over all the integers from 0 to 29, and if ith bit is set, then the number of then how I will update all the previous bits which are 1 will change it to 0, and all the previous bits which are 0 will change it to 1. Cool. So yeah, total number of elements minus the number of elements which are previously set, and then I will propagate this changes to the left and right node. Cool. So that's why I'm taking XOR, and this is the basically method to build the segment tree, and this is basically very obvious. I did over all the 30 bits, and if the value is set, then increment that we got one element which has this bit as set. Cool. And these are some method overloading, and method overloading because here we have the same name but different parameters. Then in this way I will update. First I will check whether I have some lazy value at this node or not, and if it is, then I will propagate and make this a lazy value 0 for the current index. Cool. And if this range is not the part, then simply return from here, and if this range is completely the part of required range, then I will just simply propagate the change and return from here. Cool. Otherwise, just simply make a call for the left subtree and the right subtree and pull the changes. Cool. So yeah, these are the methods of a segment tree, and here we have this our query method. So first I'm checking if the lazy value is not equals to 0, then I will simply propagate and update the current range, and then its lazy value would be 0. And again I'm checking the same thing. If the range is not the part, then simply return from here, or if the range is completely part, then here is my variable current, which is equals to 0, and then I iterate over all the 30 bits, and if the bit is set, the number of element which has this bit set multiplied by the weight of current bit, and make sure to take a mod with m, that is 10 power 9 plus 7, and finally I am returning returning this answer. Cool. Otherwise divide this range into two parts. This is for the left subtree and this is for the right subtree. Then add the answer of the left and right subtree and make sure to take a mod with m. Cool. And this is the method which you have to complete bitwise queries. So here I have created a segment tree and passing the size of this array A and then passing this vector to build the segment tree. Then this will be my answer vector. Then I iterate over all the queries. This T is the type of query. Then L to R, and this X is the element that you have to update. So if the type is 1, then we have to update this range and taking XOR with X, and otherwise we have to answer. So I will just simply call the query method of this segment tree class. Cool. And finally I'm returning this answer. The time complexity is n log of n base 2 because we are using the segment tree and efficiently performing the range update. So let's just try to submit this. Okay, we are getting the wrong answer. Okay, this is not this one, but instead we have to submit this program. So yeah, successfully submitted, and this is the complete solution for all the 4 problems. So thank you so much guys for watching this video, and have a good day.